Hello everyone. I'm going to teach you today how to apply three moments equation for a static system. Actually, in your case, like in structural analysis, we can solve continuous beams with this equation. And I'll write this equation. It's like this. So if you have two spans like this, let's say like this, okay, and it does not need to be exactly two, so you can have more than. So this is a sign of continuation, right? Doesn't matter. So you choose two spans, right? Place in which is placed next to each other, and you apply that. Let's say like this. So if this is A, B, and C, let's say this is L1 and let's say the beam is EI, okay? E1, E1, I1. So let's say that is also changed. So let's say this is L2 and this is E2, I2. So this shows some different loading, let's say like this, okay? So it completely has different loading. So what you need to solve in this beam is, so if you can find these support bending moments, right? So you can probably uh, separate each span from that support and solve just like you did in moment distribution, right? Okay, so this is given by one equation in this case. So let's say this is m1, okay? So let's say the bending moment is, so if it is continuous, sigma m is 0, right? Let's call this is m1. Let's call this is m2. Let's call this m3. Okay. So summation is 0, but these two are equal and opposite to each other, right? So for the equation, we only take this portion right here, right? So the equation we can write like this: m1 L1 over the Young's modulus and the second moment of inertia of that portion, right? Whatever comes to here, right? We first apply to this span, right? So for this particular point, that belongs to this L1, E1, and I1, right? So this part is common to both of these beams, right? So that you have both terms, which we can write like this: 2m2, right? So within brackets you have to write, because that is common for both spans, right? L1 over E1 I1 plus L2 over E2 and I2, right? So then M3 belongs to this span only, right? So you can write M3 3 L3 over, sorry, L2 E2 I2. And this is equal to, right? If you write it like this equals to 6 times, within brackets, delta 1 minus delta 2 over L1 plus delta 3 delta 2 over L2 minus, inside that brackets, A1, simple A1. I'll define these terms, don't worry. E1, I1, L1 plus A2, A2 into A2, simple A2 over E2 I2 L2, right? This is L2. Okay, so we close the bracket and close the furthermost bracket. So now you have these brackets. Okay, so don't be, so this bracket is applied, 6 is applied for all these portions, right? Okay, so this is 3 moments equation. So you know M1 is the support bending moment, right? So I'll give you the sign convention later. M2 is M1 is the bending moment, L1 is the length of the beam meets M1, right? So that is L1, right? And E1, this is E1, my mistake. Okay, so mistake. So then M2, then this is 2 is there, originally there, M2 within brackets. So that meets, that connects these two spans, L1 over E1 I1, L2 over E2 I2, right? So that is there, and that's done. These two terms, M3 is the right corner, right? So you only can choose two spans, right? Okay, so if you have more than two spans like this, right, so you have to take these two spans and apply, then you have to choose these two spans and apply, again you have to apply these two spans and apply, so altogether you have to apply it 3 times, right, by taking 2 by 2, right, 2, then these two, finally these two, right? So there will be common variables you will encounter. So when you apply to this portion, this is L1, this is L2. When you apply to this portion, this is L1, this is L2. When you apply to this portion, this is L1 and this is L2, right? Correspondingly, E1 and I1 as well, right? So L2 is the second, and E2, I2 are the same. Delta 1 is the support settlement, right? If you don't have any settlement, that's 0. If you don't have any settlement at M2, that's 0. Likewise, 3 is the support settle. Delta is the settlement at the support, right? So this just look at this, just look at this. So that what will give you, so delta 1 minus delta 2 will give you the relative displacement, right? Relative displacement divided by the length of that span, right? Okay, so A1 is the area of the bending moment, simply supported bending moment diagram, right? And this distance to centroid from one end, right? We can discuss within an example, right? So this is the area of the simply supported bending moment diagram into the distance to its centroid, right? Over E1, I1, L1, right? So we shall discuss this example. Shall we take this? Right. So this is L and this is also L. So let's consider EI is a constant, right? So we know that this is a pin end, right? This is also a pin end, so that we know what? We know what, right? So the bending moments at a pin or roller end is 0, right? So if you consider M1, that's 0. If you consider M2, that M3, that's 0, but M2 is there, right? But sigma around this one is 0, right? The summation of bending moments about B is 0, but you have a bending moments, you have a bending moment that is equal and opposite, right? Okay, that's a hogging moment, so which you need to find. Let's call this M2, right? Let's call this, for now we call this M1, M3. So we'll apply the equation. So M1 over EI, because that is same, right? And 2M2, right? L1 over E1 I1. In this case, everything are same. Okay. And M3 over EI, right? Is equal to 6 times. There are no settlements. So the first term and the second term is 0. So you need to consider the simply supported bending moment diagram. For each case, that will be similar, because both having similar load of uniformly distributed load. So that will give you a bending moment like this. So this is W L squared over 8. Right? So this area is given by, so the distance to centroid is, so this bending moment curve is symmetric. So the distance to centroid is lie in this lie on this line, right? So that the distance to centroid is L over 2, right? So that is simple A. Simple A is L by 2. So we take hogging bending moments positive, okay? That's our sign convention, hogging positive. hogging positive, right? So in the middle of this beam, you have sagging bending moment. It try to bend the beam towards the downward sides, where you have tension at the bottom of the beam and the compression at the top of the beam. So this is a sagging bending moment, right? So your area will be negative. Why? Our sign convention is positive, right? Okay. So if this is your x line, this is underneath the x line. This is sagging. If it is like this, that's hogging, right? So area is, so if there's a curve, that's the area is 3/2 times B H, right? So B is the length, H is the height, right? So that's gonna give you B is the length is L, H is the height, bending moment, WL squared over 8. So that's capital A, capital L, okay? So this will give you for WL cube over 2L, right? So that you can go ahead. This is the area, right? This is the area. So these two parts will be the same, right? Area is same. The distance to centroid is same. EIL is same. So I will write 2 times this term, okay? That is negative, right? Yeah. Negative 2 times, because these two will be the same area. A1, A2 are same, right? Because the same arrangement of each span, same length, same EI, and same distance to centroid, right? From one of the corners, right? If it is simply supported, right? So my answer is WL cube over 2L, and A is L by 2, EI L, right? So from the answers that you can take, yes, you can cut these two together, and L also, and you can cut EI from the whole equation. If EI is equal, you can cut it easily, right? Otherwise you can't. So we know that M1 and M3 are 0, right? Right, these are pin supported ends, so the bending moments are 0. So you will only be remaining with 2L. 2L times 2M2 means 4M2 is equal to 6 times negative WL cube over WL cube over 2L, right? So this will give you 2, and M2 is what? Oh, sorry. Since this area is negative, right? Since this area is negative, because this is sagging, so there should be a minus sign here, right? There should be a minus sign, so that is positive, right? Why? Because this area is negative. Why? That is sagging. If it is hogging, that's positive, right? Okay, so right, so it's going to be W L squared over 8, the answer, right? So there are few implications, right? So the application of three moments theorem is as follows. Uh, if you have, so these are the preliminary stage, right? So if you have some sort of arrangement like this, let's say this, right? So first you can take these two and apply. So let's call this M1, M2. Don't worry, I'll do an example. M3 and M4, right? So for the first time, you take these span and apply the equation, and then you take the remaining spans and apply this one. Okay. So similar to what we did, if you have any settlements, you can even compensate with this equation, right? So what we know is at the ends M1 and M4 are 0. So you will have two equation and two unknowns, M2 and M3, right? So you can solve it. So if you have any, so when the number of spans are increasing, the computational will be high, right? So the computational effort will be high. And if you have something like this, right, some overhanging span, right? So here, you know, M1 is 0. That's the end. M2 will be there and M3 will be also there. But compared to this, now M3 is also not 0, right? So, but you can find M3. How? If you have any loading on this span, so because this is determinate part. So M3 will be the load into this distance, right? So this is going to bend this beam in this way. So the resistive moment M3 can be found by, if it is P, this is L, P into L, right? M3 is P times L. That you can easily determine. If it is a, let's say, if it is UDL, don't worry, W, let's say the length is L, so the total load is WL, and multiplied by the lever arm. Lever arm is L by 2. WL squared over 2. That is the M3, right? That's hogging, right? That's hogging. So it's going to bend this beam in this way. So the resistance will be in this way, hogging, right? So whatever you see, right? So if it's like this, that means hogging, right? If it's like this, right? That's sagging, right? So this is also can be done. Then the special case, if you have a fixed support. So what can you do? If you have a fixed support, right? Imagine these are your supports and there's a fixed support. So at fixed support, what we do is we take an imaginary span that we copy this span, right? This span only, right? Let's call this A. So this is the copy of A, exactly same length. Let's call this A dash, right? Let's call this O, right? Let's call this O. So this, for this span, this is an imaginary one. We set EI as infinity. EI goes to infinity, right? So stiffness is infinite, right? So that you can take. So what we do is, if there are, so you can only have two fixed support at the ends, right? So if you have it, what you need to do is you set it as a mirror and mirror the span which is connected to that, right? And most importantly, set the EI to infinity. If you have a fixed support here, right? Let's say if you have a fixed support here, so what you need to is B. So if this is L2, if this is L0, let's say L0, this is also L0, this is B dash, right? So you don't need to worry on these support conditions. I'll show you why. I'll show you why. So you don't know the position, what is this, right? So I'll for a moment stick with me, right? So this is L0, so we call EI to infinity, right? So we can apply this into an equation, right? So, and now you have some additional parts, right? If you have a beam like this, you have to apply three moments equation to, so doesn't matter, whatever occurs, you apply three moments equation only to two consecutive spans, right? To apply these two, then for these two, next for these two, and finally for these two, right? So if you have fixed supports, that's a lot of work, right? So we'll do an example with a fixed support. So let's say your beam is like this, right? Right. So the length is 8. This length is 10. This length also 10. Right. So let's have a uniformly distributed load, right? W is 2 kilonewtons per meter. Okay. Okay. And you have a point load of 8. Okay. And another distributed load here, that is also 2 kilonewtons per meter, right? So this is a fixed support. Let's call this B, C, D, E, right? So the reason I start from B is I can give this imaginary point to A, okay? Or else you can start it A, B, C, D, then this is B dash, right? Doesn't matter anything, right? So another thing, so E is same, Young's modulus is same, it's the same material, right? Same material, but the cross-section area varies. This is 4i, this is 5i, and this is also 5i. Okay, so now what you need to do is you have to solve it using three moments equation, right? So first thing is you need to determine which category it falls into, right? So it does not fall like this, it does not fall for this, it falls like this. That's a fixed condition, right? So what you need to do first is to extend this one, to take the mirror image. Exactly, this is A, right? So 8 meters, you don't need the loading. You don't need the loading. What you need to do is EI set it to, you don't know the I value. You don't need to worry on the I because EI for this part is infinity, right? Okay, so I'll call this E dash, okay? No, not E dash. Just keep it in mind, EI for this part is infinity, right? Because it's an imaginary part, right? So you can apply three moment equation, right? For ABC, right? For ABC, you can apply the three moment equation. So it's going to be like this, right? So let's call this MA. Okay. You don't know the support conditions. And then MB plus 2 MB, right? So again, L over this EI, okay? This EI is infinity. I will write infinite. Otherwise you will be confused. So if it is infinite, please write infinite, okay? Plus, otherwise you will be confused with other EI, right? So this next part is also 8. So I write in different color. 8 over 4i into E, 4EI. 4EI into MC times L2 over EI, right? So this is 8 over EI. Same for EI. Right? This is why I told you, you don't need to worry on this conditions or whatever, because EI is infinity. And when you divide by, so you don't know even what is MA, right? That's an imaginary one. But if you divide anything by infinity, that's going to be 0, right? So you don't need to worry at all, right? So there's no, so this is rigid, right? Flexure rigidity is 0. So settlements not occurring at each of these places, right? Not settling. So these first two terms will be 0, right? You have to reduce. So you remember a1 over, again you have ei term that's going to be infinity for this beam, right? And you have another a2 a a2 over ei l, right? So this is going to be 0, this is 0, so you will obtain, so 8 over 4 means 2, 2 into 2, this 2 will be multiplied by 2, so there's going to be 4mb over ei. This is 2mc over ei, so there's 6, okay, 6 into minus, so this 0 I didn't write it, I write this part, so this is also 0. Why? For the first span you have something called ei term, so this is going to be infinite for the first term, so you whatever the other values, if you divide something by infinity, that's 0, right? So the other part, it's sagging, right? So for the sagging, you obtain the value earlier, right? If it is simply supported, so you remember minus wl squared over wl cube over 2l, and multiplied by l by 2, that's the simple a, right, divided by ei into l, right? So this minus minus will be positive, so this is 2 into 1l will be cancelled, ei will be there, right? So l cube means l is 8 to the power 3, right? 8 to the power 3, okay? So, oh, sorry, this is 4 ei, right? For the second half, that's 4 ei, right? Because that's 4i, right? So the term 4 is there, right? So when you simplify this, you will get the answer as what? You will get the answer as the answer is 8 to the power 3. So this is 2, right? That's going to be 3, right? So and finally you will be remaining with, so you can even cut ei,
and you take 2 out, 2mb plus mc is equal to this, right? And that's going to be 64 into 4, right? 64 into 8. I did not simplify because this 8 can be cancelled by these 2, 4. Right. So then, oh, I forgot these 2, right? So this 3 is there, and 12 into 2, that's going to be 24. So if you cancel it, it's 8, right? So you can cut this 8 by this 8. So 8 into 4, that's going to be 32, right? So that's our first equation, 2mb plus mc is 32, right? So we go to the other case. So now next we take these 2, right? These 2 spans and write the equation. So I'll write it here. Write it here, I'll erase this one. So hope you can see the previous one. Okay. So I have this. I will now apply for BCD, right? So for BCD, if you apply, you have MB, L is 8, over EI is 4EI. Plus now the middle one is C, right? 2 MC 8 over 4EI. So 8 is this length divided by E into 4I, right? So then the next 8, or sorry, that's 10, right? L is 10 divided by 5EI into MD, that's L is 8, sorry, L is 10. 10 over 5EI. Okay. So again, the settlement terms are 0. So you can straight away write the bending moment part, right? Negative. Again, these 2 are sagging, right? These 2 are sagging. So that's also negative, right? A1 is, so you remember, if this is, so you remember the area, 2/3 L into WL squared over 8. WL squared over 8. 8 is the bending moment. If it is a point load at the middle, right? So this, you know, PL by 4, OS WL by 4. So that's a triangle. So the area is half L into WL by 4, right? So that's give you WL squared over 8. This will give you WL cube over 2L, right? So the area is WL cube over 2L. The distance to centroid is L by 2. Sagging, that's why it's negative. Divided by EI is 4 EI. L you can substitute later for the second. So this is L1, I would say, okay, because L are different, okay. L1. So then the other term, so that's going to point load. So that will give you W L squared over 8. That's the area. Again, the distance to the centroid is 2, L by 2. So this is 5 EI. L. I would say this is L2. Okay. So once you simplify this, okay, so L1 is 8, L2 is 10, W is, this is the uniform UDL, this is the point load, this is also 8, and L2 you know 10, L1 is also 8, right? Other things you can simplify, right? MB is non-zero, MC is non-zero, MD is non-zero. So you will obtain an equation like this. When you simplify, right? Simplify it and see, you will obtain as MB, because you can straight away cut EI from the equation. Right? So be very careful when you are especially working with symbols, because here it's L cube, here it's L squared, right? And this is the point load, that would be capital W, something like that. This is simple W, so that's a UDL, right? So when you're working with especially symbols, be very careful. So you will get an equation like this for MC plus MD is equal to 62. Okay, this is your second equation. $62, right? So, and finally, you will go to CDE spans. So you go to these two spans, right? And apply. So that's going to be MC into 10. So both spans length is 10 meters, okay? So over EI is, so the first part is 5 EI. Second part is also 5 EI, okay? So 2 MD is the middle point. So that's going to be 10 over 5 EI divided by this 10 L over 5 EI plus L over 5 EI, right? The same thing, right? Plus ME 10 over 5 EI, right? Again, there's no settlements. So the first terms are first two settlement terms are 0. So I won't write that. I will not write that. So then there will be negative this term, right? I will write this term only. I will write this term only. These two terms are 0. This is 0. This is 0 because each settlement is 0. Oh, I think I missed that, right? Yeah, I have to write it again. So what you need to do is you take consecutive two spans and apply this in order, right? From left to right, right? So this. So I will not write the settlement part, 0. So there's a load here, right? So the point load. So you remember that's W L1 squared over 8. The area of the simply supported bending moment diagram, right? So distance to centroid is L1 over 2 divided by, so 5 EI L1. And L1 is similar to L2 as well, right? So you can write the same L, okay? No problem. L1 is 10. L2 is also 10, right? So I will write L1. So this is sagging, so this is negative, right? This is also, the second one is also negative, so that's UDL WL2 cube over 12. So that's the area of the curve, right? You remember? And then this is distance to centroid. If it is symmetric, that's going to be L by 2, right? 5 EI L2. L2 is also 10. Right? This W is 2. This W is a point load, that's 8. Right? So you can cut this EI away from the whole equation. And what you observe is ME is the end pin support, right? So that's going to be 0. End moments. So if one span only connected, simply supported at a simply supported end, so you know the bending moment is 0, right? So once you simplify this, you will obtain an equation like this. MC, so I'll write this here, MC plus 4MD is equal to 80. Okay, this is 80, right? So from these three, so you only have B, C, and D. So you have three equations. You can solve this. Okay. So I can get rid of MC from first and third equation. Or else, yes, I can get rid of. So I will yeah, I will reduce 1 by third, right? So that's going to be 4MD minus 2MB is going to be 48. So that's going to be, so you can divide it by 2. This is going to be 24, because the entire equation can be divided by 2, right? So then I will multiply this equation by 4. So that's going to be 8MB plus 4MC is equal to 128. And now I have 4MC term. I can reduce second equation. I'll call this fourth equation. From fourth, I will reduce the second. So 8MB minus MB, so that's going to be 7MB. Minus MD, because 4MC getting cancelled. Is going to be how much? 66. So because there's 2MD, I'll multiply this by 2. So that's going to be 14 is 2MD. And this is going to be 132, right? So when you add these two together, 2MD will be cancelled, right? So you will remain 13MB is equal to how much? No, you need to add these two, right? When you add these two, so you will obtain 156, right? Yes. So you will obtain MB as 12, right? Then MC as 8 and MD as 80, right? So here are the values, right? So these are only support bending moments, right? Just remember you have just like the moment distribution, right? Just like the moment distribution. So you know MB is 12, MB is 12, MC is 8, MB is 12, MC is 8, MD is 18, right? And ME is 0 because that's the simply supported end, right? So this is the support bending moment. And now you have solved the support bending moments. So you can separate each span from the corresponding support bending moment and find the shear force values, considering each span only, right? For example, so you can determine the shear forces if you want, right? So to construct the full bending moment diagram, you need to consider the simply supported bending moment. So you have a UDL. So you will have a curve like this. This is a point load. You will have something like this. There's a UDL. So in my moment distribution lecture, please watch it. I have explained this clearly, right? How to draw this. So this is only to, this is the load, simply supported loading, right? So this part is, the red part is negative while the blue part is positive, right? Hogging moments are positive, right? As I told you. So the remaining part will be the bending moment curve. This is the, this is your bending moment curve final. Okay. So this depends on your value, because if your loading is not so high, probably this curve will be look like this. It won't get past the x-axis, right? Like this, it won't get past the x-axis. It will end something like here. So it depends on whether this value is, whether this height is larger than this or less than this. Okay. So I have clearly explained in this. Please watch those videos. So that's how you use the three moments equation to find any bending moment of a continuous beam like this, right? So first thing you need to do is uh, make the structure look like either one of these, right? Then apply from each to span from left to right, right? Finally, solve for the bending moments. Thank you.